Hello, I'm Dr. Malescu, and I'm going to be presenting respiratory system. So I wanted to show you this model that I have here and all the components of the respiratory system. So the first thing I want to point out is, although it's not part of the respiratory system, what sticks out like a sore thumb, right here it is, there's your thyroid. All right, so I wanted to show you that there's your larynx, and you can see the tracheal rings real close here. So that's your trachea. And follow it down, and it divides into the left and the right bronchus. And you can see here the aorta and the aortic arch, all right? And you can see the superior vena cava, and going off to the right, the brachiocephalic, pretty cool stuff that you can see. But bottom line, I'm gonna stick with showing you very close up the terminal branches of the bronchioles, and you can see the veins and the arteries. So remember the circulatory system in the pulmonary circuit, the veins are carrying oxygenated blood, right? So, and it's returning via two pulmonary veins from the left lung and two pulmonary veins from the right lung. Okay, so that's what you're seeing there. I also wanted to show you the alveoli where gas exchange occurs. So these are the alveoli, and you could take a look and see in great detail here. Oops, let me just remove the bottom and let me show you the capillaries. So you can see every single alveolus, plural alveoli, has a bed of capillaries. And so remember, because we're talking about the pulmonary circuitry, right? The pulmonary artery is carrying deoxygenated blood, and it becomes a pulmonary arteriole, and then eventually feeds into the capillaries. And the capillaries are intimately adjacent to these alveoli. So at that level, on the arterial side, right, the pulmonary arterial side, there's a lot more CO2 than O2 because it's coming back from the right side of the heart. So that's where we go down the pressure gradient from high to low with that particular PCO2 is high in the arterial end of the capillary, and it's moving across to the alveolus, and the alveolus picks up the CO2. Meanwhile, the PO2, the pressure is higher on the alveolar side, so it goes down the gradient from high to low into the capillary level venous side, okay? So that the pulmonary veins become the pulmonary veins bring the oxygenated blood back to that left side of the heart through the left atrium and ventricle. All right, now the topic of ventilation, which is what the whole purpose of this video is to prove to you with this little device here that when, and I'll put it on my shoulder, when I do this, see, and I pull down, that, imagine that that's your diaphragm. And as I pull down, you can see that the lungs are expanding, okay? So when you pull that dome down, okay, the lungs are expanding, the volume goes up, and the pressure goes down, air flows in, okay? And so with that said, I'm gonna show you the blackboard because I really wanna make sure that you understand this. So on this side over here, we have inspiration, and the diaphragm is going down. That's why you see the arrows going downward. So diaphragm drops, the lungs expand. The arrows represent that the lungs are expanding, and you can see here that the pressure is going down and the volume is going up. Why is the pressure going down? Because the lungs are expanding. So air naturally flows in. So the formula over here is PATM is greater than P pull. All right, so let me show you that. Let me lift it up. Okay, so here, the atmospheric pressure is greater than the pulmonary pressure. Now let's look over here, and we can see that on this side, we have the opposite. The arrow showing upwards like this shows that the diaphragm is coming back up, the lungs are recoiling, the arrows are pointing towards the lung, so therefore pressure is going up and volume is going down because the lungs are recoiling back to the original position. Therefore, air flows out. All right, so that PATM, all right, so in this case, we have the opposite. We have P pull greater than PATM, meaning the atmospheric pressure is less than the pressure inside the lung, P pull. All right, so therefore air flows out and we get rid of the CO2. And that's how it works. Now, the last topic that I discussed earlier, and I wanted to make sure that you guys really, truly understand, and let me move my camera here, and I'm going over it now, is that we have to understand ventilation, which is the process that I just showed you, mechanical ventilation. As you inhale, diaphragm drops, lungs expand, right, all the way up to the apex, because your external intercostal muscles are contracting. Even your scalenes, if you remember from A&P1, your scalenes are lifting up the clavicles so that the apex of the lungs expand. So lungs expand, volume goes up, pressure goes down, air flows in from higher concentration outside to a lower pressure gradient inside. So that's how we get that higher concentration of oxygen, all right? Because inside, you know, the pressure right now is low. Lungs are expanding. So, you know, the pressure gradient, that's how we always operate. So therefore we go from high pressure to low pressure down that pressure gradient. So air flows in and we bring in that oxygen. All right, so that's ventilation, inspiration. Now expiration, the external intercostals relax, the lungs recoil back to the original position. Okay, diaphragm goes back to its original dome shape. Pressure goes up because the lungs are recoiling. So now P pull, the pressure inside the lungs is higher than the pressure outside, atmospheric. So the CO2 is pushed out during expiration. So that's ventilation. External respiration is the process of gas exchange between the capillary and the capillary networks and the alveoli. So that again, it's a pressure, gases, individual gas pressure. So CO2 levels are high on the arterial end of the capillary. So therefore the CO2 diffuses across from high concentration inside the capillary to lower concentration in the alveoli. So obviously we get rid of the CO2 and then we exhale it out. Well, now what about the O2? The O2 is picked up via diffusion. Higher concentration inside the alveoli, since you just breathe in, right? Inspiration. And it is a lower concentration in the capillary level, so it's going to go down that gradient, that pressure gradient from higher pressure of oxygen inside the alveolus versus lower levels of oxygen in the capillary level. So we go down that pressure gradient from the alveolus to the capillary. In it flows, and now on the venous end, we're picking up all that oxygen, and the capillaries are exchange vessels. That's what we just did. But each one of those capillaries carries out one red blood cell at a time, and all those red blood cells have 4 binding sites for oxygen, right? But there's 4 million hemoglobin molecules in a red blood cell. So that's a lot of oxygen. Just one red blood cell can pick up 16 million oxygen. So now we're traveling with oxygenated blood. Pulmonary venule, pulmonary vein, and now the 2 from the left lung, 2 from the right lung, entering that left atrium, left ventricle, and the cardiac cycle is going to pump out that oxygenated blood throughout the aorta, aortic arch, aorta, and systemically throughout all tissue. Final step, okay, is internal respiration. What happens when the blood gets to the tissue? Same thing, it's pressure gradients. So now we have the opposite of what we had in terms of external respiration at the lungs. Now we've got the opposite. We've got basically the oxygenated blood at the capillary level is going to diffuse the oxygen across the membrane via diffusion. Okay, oxygen is going to go from a higher pressure to a lower pressure down that pressure gradient. Meanwhile, the cells are building up toxins, including CO2. So higher level of toxins and CO2 inside the cells. So it's going to go down that pressure gradient. CO2 is going to go down that pressure gradient from a higher level of CO2 inside the cell to a lower level of CO2 outside of the cell, meaning in the capillaries. And so now we've got deoxygenated blood picking up that CO2, and CO2 is carried in the blood, transported in the blood in a number of ways. Either it's carried out by the hemoglobin molecule, okay, carboxyhemoglobin, or it's bicarbonate. And so there's different ways that we can carry out that carbon dioxide, all right? But initially, if it's bicarbonate, it'll convert to carbon dioxide when it gets to the alveolus. And that basically is the process of respiration. Again, the four main steps are ventilation, which is the mechanical, Boyle's law. Lungs expand, inspiration, lungs recoil, expiration. External respiration is the gas exchange between CO2 and O2 at the alveolar capillary level. Transportation is the systemic arterial system delivering oxygenated blood, and the venous system delivering deoxygenated blood back to the right side of the heart. Internal respiration is the gas exchange between the capillary and the tissue so that we can pick up the O2 at the cellular level and dump the CO2 into the venous circulation and back to the right side of the heart. And that there in 11 minutes is a respiratory system. Hope you enjoyed this video. Bye. See you next time.